What's up, guys? We're going to be continuing right where we left off with applications of differentiation. So we're going to start back up with that second derivative test and see sort of what it tells us about different aspects of the graph of the function, which namely in this case is going to be focused on concavity. So I've actually already taught you guys this before, but we're just going to sort of go over it, just have a nice little review day. So this is a quote from Edward Frankel. He's a modern day mathematician. He's still living today. He actually teaches at UC Berkeley, if any of you guys are thinking about maybe applying or going there. I think he teaches, well, last time I checked, he teaches something like multivariable calculus, which is sort of the next level after what you guys are taking. So he says, mathematics directs the flow of the universe, lurks behind its shapes and curves, holds the reins of everything from tiny atoms to the biggest stars. And that's a really powerful quote just because of how true it is. I mean, mathematics, we use it on the tiniest of scales, but we also use it on the astronomical scales to analyze the hugeness and vastness and workings of the universe around us. So it works on all scales. And again, that's kind of mysterious why something that you guys can learn in high school can be so powerful, right? You would think that you would have to learn something really, really complicated to analyze the entirety of the universe, but it turns out it's just mathematics. And the better you get at it, the more you can understand what's around you. So fun fact about this guy, he's actually part of one of the reasons why I got into teaching. So he wrote a book called Love and Math, which when I was a senior, like many of you, I was sort of walking around at Barnes & Noble, didn't quite know exactly what I wanted to do. I think teaching was on my radar, but I didn't know for sure. And I just knew I was good at math. That's kind of all I knew. So I was in Barnes & Noble, and I just kind of stopped by the mathematics section, and I came across this book, and it's got a really, really iconic cover. It's got Escher's Starry Night, or is it? It's either Escher or it's, or maybe it's another artist, but the Starry Night photo that looks kind of out of focus almost. Just Google it if you don't know what I'm talking about. But I just found it fascinating that he would have love and math in the same sentence on the title of his book. And it turns out his book is really great. It's a memoir sort of about his own life, and he also sprinkles in some higher level math that you generally don't tend to see in high school math, things like abstract algebra and group theory. And they're actually ideas that you guys could understand if you really take the time to learn them. And they're also pretty mind-blowing too, the fact that algebra works with things that are not even just numbers. They work with all kinds of other objects. So that's all I can really say there. So what did we learn last time? Well, we learned the first derivative test. So this test sort of allowed us to figure out if we had relative maxes and relative mins, right? And so what we would do is if we had a critical value, critical point, let me come up with an actual function here. Let's say f prime of x was x squared minus 1, right? Some critical points would be -1 and 1, right? And so what we would do, how do we know which one is actually going to be a min or a max? Because if you notice, if the derivative is x squared, the original function is probably x cubed, so it's going to have one min and one max. How do we know which is which? Well, what we would do is we'd sort of make like a little real number line to ourselves, right, with the critical points on it. And we would test to see what the first derivative spits out to us on the left and the right sides of each of those critical points. So, you might plug in a 0 there, you get a negative first derivative. If you plug in a -2, you're going to get a positive first derivative, and over here you'll get a positive. And so what we said was, well, these tell us the slope of the tangent line to the left and to the right of each of these points, right? So we have a positive slope here, we flat out to 0, and then we have a negative slope over here. So that looks kind of like some kind of hill, right? So we have a relative max at -1. And then over here, right, we have a negative slope, right, in this region. We have a 0 slope at 1, and then a positive slope after 1, right? So we have some kind of valley, right? And that's the point we're concerned with. So this is a relative minimum, right? And so that's the first derivative test. You're testing the slopes of these tangent lines. You're sort of trying to gauge what are they doing on the left and right sides. We also went over the second derivative test, mainly, again, to evaluate these critical points. And this one is even easier than the first derivative test, if you can do it, right? Because all you have to do is, in this case, you would find the second derivative, f prime prime of x, which in this case would be 2x, right? And then you would plug the critical points in, right, into this second derivative function. So the second derivative at -1 is -2, which is, we said it was concave down, right? The fact that that answer is negative tells us that the graph sort of curves downward. And then over here, we plugged in +1. We have 2, right? And so positive answers out of the second derivative tell you concave up. So this is when graphs sort of curve upwards. And so those are the two tests you can run to determine if you're looking at a relative max or min if you don't have the graph in front of you, right? It's very easy to see it on the graph, but if you don't have it, those are the tests you would do. And so you can also use the second derivative test in general just to see what kind of concavity the function has. Concavity is just sort of a specific word for curvature. So we're going to determine the intervals for concavity, right? Same way we determined intervals for increasing and decreasing. It's a very similar thing, right? Except we're using the second derivative now. And we're going to use this to find inflection points. You guys have already seen how to do that. And relative extrema, again, this one you've also seen. So really the only new stuff is probably the intervals of concavity portion of this lesson. So here's what concavity means. So we say that the graph of f is concave upward on I when f prime is increasing on the interval. And we say it's concave downward on I when f prime is decreasing. So it's probably helpful to draw some pictures here, right? So how do we really know that something like this is concave down? Right, so we know that's kind of what it is. In this case, it's a lot more obvious, but in other cases, it might not be. Well, you determine this by looking at the slopes of the tangent lines and see if they're increasing or decreasing. Right, so if I draw a bunch of tangent lines, right, all along this function, right, the slopes of these tangent lines start from some sort of big positive number that decreases. Eventually it goes down to something like 0, maybe right around here. And then the slopes turn into bigger and bigger negative numbers. Right? So if you were to imagine, maybe this slope is like 4, and this one is maybe 1, and then 0, and then -1/2, maybe -2 here, -5 here, right? So overall, the slope is decreasing. It's going down, and so that's how we say this is concave down. So when in doubt, look at the slopes, right? And same thing if we had concave up, right? So look at the slopes of these tangent lines, right? See what they're doing? Well, they seem to be increasing, right? We start from some big negative number, it gets smaller, it goes sort of to 0, we get a positive and a bigger positive number. Right, and so if you think about the numbers involved here, we're increasing the slopes, right? The slopes are increasing, so concave up. So let f be differentiable on an open interval I. If the graph of f is concave upward on I, then the graph of f lies above all of its tangent lines on I. Interesting. So I guess this is another way to see it too, that the graph is physically above the tangent lines, right? So like this piece right here is actually on top of the tangent line here. Right? So maybe that's another way to see it. Whereas if you had a concave down graph, right, which is actually on top, well, the tangent line would look something like this. Which is on top? Well, the on top part is the tangent line. So this would be the opposite, concave down over here. So I guess that's another rule of thumb you guys can use. Actually, I'd never thought of that before. But this one is actually pretty easy to use. So feel free to use it. Yeah, and we have an example of concave down over here, right? So f prime is decreasing. The slopes of the tangent lines are decreasing. So I'll move on here. So to find these open intervals, you need to find intervals on which f prime is increasing or decreasing. They're kind of just restating themselves at this point. So you're just looking for those increasing and decreasing intervals of f prime, right, the derivative. And if we look at this example over here, right, so like right here, right, the slope is 0, and then it looks like it starts to decrease and decrease, and then something changes over here. So let's say we have 0, maybe -2, -2.5, right? And after this point, right, we have, let's say this is -2.5 slope. Our slope starts to increase. So maybe this is -2 and this is 0, right? So what we call the thing in the middle, that's our inflection point. And notice, some of you guys may have noticed this or not, but inflection points have nothing to do with the first derivative. They don't have to have a first derivative of 0, because look at, in this case, right, at this inflection point, the slope is not 0, right? So they don't have any connection to the first derivative. It's all about the second derivative. And so notice what's happening here. So let's see, what are they trying to say with this graph? They're graphing the derivative of f over here, and if the derivative is negative, or if the derivative is negative, that means the slope of the tangent line is negative. And notice how this entire part of the graph here is under the x-axis, and all of these slopes over here are negative, right? And when the graph goes above the x-axis, this is the graph of the derivative, the slopes of your tangent lines also are positive, right? Same thing over here, right? Over here, the slopes of the tangent lines are positive. Right, so the graph of the derivative can actually help you really analyze the original function too. So test for concavity. You guys have kind of already seen this before, but here it is officially. Right, so when f double prime is bigger than 0 for all x and I, then the graph is concave upward on that interval I. Right. If it is negative, less than 0, right, then the graph of f is concave downward on I. So that's the quick second derivative test that we've kind of been doing so far to figure out if we have a relative max or relative min. So to apply this theorem, look at the x values at which f double prime equals 0, or where the second derivative does not exist. So use these x values to determine the test intervals. So same kind of steps as what we did with the first derivative test, almost. So determine the open intervals on which this graph is concave upward or downward. Right, so one natural thing we want to do here, let's go ahead and take the first derivative, see what that is. I'm going to use the quotient rule here. So derivative of 6 is 0, right, times the second, minus the first, which is 6, times the derivative of the second, which is 2x, all over the second squared. Right. And in fact, well, maybe I'll expand that out. But what's nice is this first term is 0, right? So that's good. And we end up with negative 12x over x to the fourth plus 6x squared plus 9. And so to use this test, we have to take a second derivative, right? So we have to take our answer that we just got, take another derivative, and see what that gives us. So that would give us negative 12 times x to the fourth plus 6x squared plus 9. Okay, so derivative of the first times the second minus the first, so that's going to be negative 12x, times the derivative of the second, so 4x cubed plus 12x, all over the second squared. So this part over here. Nice. Okay, so this is going to be kind of a mess here, so let's see what we can do. Let's clean this up. We have negative 12x to the fourth minus 72x squared plus minus, right? 9 times negative 12, so that's minus 108. Over here, I'm going to go ahead and make this a positive just to make our life easier. We end up with 48x cubed plus 144x over this thing right here, squared. So really the question here is, when does this second derivative equal 0? And it's not super obvious how to do this algebraically. Let's see if they have a nice solution here. Yeah, so I'm thinking that on this problem, you would have to use a calculator to sort of analyze the outputs here. I don't think I'd ever give you guys anything like that without a calculator. Even I can't see a way to factor this or use factoring by grouping, anything. This one's kind of a beast. So use a calculator there. And what they do is they set up these little intervals, right? So this is very similar to how we set up the real number line with that first derivative test, right? So they had critical values at -1 and a 1. And what they found was the second derivative, f double prime of x, it looks like was positive over here, negative here, and positive there. And so what they're saying is that over here we have our concave up interval. Over here we have concave down. And over here we have concave up again. Right, so they're just using this second derivative to figure this out. And so, by the way you would actually write these intervals, yes, you can sometimes write them this way, but if I were to ask you just what is the interval on which this function is in concave up, so let's make a note over here, concave up. The way I want you guys to write this is using interval notation. So in this case, you would say negative infinity to -1, union 1 to infinity. And then we would say we have a concave down interval just for -1 to 1. Points of inflection. So you can use the second derivative to also find these as well, like we've seen before. But what do they actually describe? They describe when the concavity changes, right? So when the graph of your function changes from concave up to concave down, right? And that can be kind of a tricky thing to see sometimes. And notice how we have very different cases here, right? This is when f prime of x is some positive number. Over here we have the first derivative f prime of x equals 0. Over here would be a case when the first derivative is undefined, right? So just to be clear, the first derivative has nothing nothing to do with the point of inflection, right? So the point of inflection only concerns itself with concavity. So like, again, right, look for what the tangent lines are doing, right? This is concave up because they're increasing. This is concave down because they're decreasing, right? And you can do similar things with these examples over here too, right? Tangent lines, the slopes there are decreasing, and then over here the slopes are increasing. Right? So it all has to do with how the slopes are changing. So the definition of a point of inflection, I may have already said this, let's see. If the graph of f has a tangent line at the point c, comma, f of c, then this point is a point of inflection on the graph of f when the concavity of f changes from upwards to downwards. Yeah, no, exactly what we've been saying this whole time. Here's a little theorem. So if that c is a point of inflection of the graph of f, then there's two cases. So either f double prime at c is 0, or that second derivative does not exist. So that's a little theorem for you. So let's determine the points of inflection at for a function like this. Let's go ahead and take the first derivative. Let's see what that looks like. It's going to be 4x cubed minus 12x squared f double prime of x. So the second derivative, what is that going to be? It's going to be 12x squared minus 24x. Right, so this is what we're going to be mostly focused on. So we can factor something out here. Right, so 12x can be factored out. And so we have x minus 2 over there. So there's really only two sort of critical values here, right? We have a critical, I guess we could call them critical points, right? So critical points, we have 0 and we have 2, right? One for each of those factors. And what we might want to do, just to check, right, is sort of see what the second derivative does to the left and to the right of these points, just to double check ourselves. So 0 and 2. Well, if I plug in a 1, I'm going to get, let's see, f double prime of 1 is going to be 12 minus 24, which is going to be negative 12. Right? And so our second derivative is negative here. Let's plug in a negative 1. Right? So we're going to get 12 over here and then plus 24. So it's going to give us 36, so that's positive over there. F double prime of 3 is going to be, let's see, 9 times 12 is 108, minus 24 times 3, which is 72. And that's going to give us 36, it looks like. So yeah, another positive answer. So just to recap, what we're putting here is the f double prime output, right? Positive and negative. So this would mean over here we're concave up. Over here we're concave down. Over here we're concave up again, right? And so we can definitely clearly see that these are inflection points. Inflection points, right here and here, because the concavity of the function is changing there. So let's see what they say here. So here they have the original function graphed right here, and they have those 2 points of inflection. Notice they're kind of like different cases, right? Like over here we have sort of a slope of 0, right? And over here we have a negative slope, but these are 2 inflection points, right? Because, right, we have concave up sort of for this part of the graph, right? You can see that it's sort of curving upward. Same thing to the right of this inflection point over here. Right? And then we sort of have a concave down portion right here, right? That blue part. And this inflection point over here is kind of one of the trickier ones to see. But the more practice you guys get with this, the easier it'll be to see them. So yeah, points of inflection. The converse of 3.8 is not generally true. So it is possible for the second derivative to be 0 at a point that is not a point of inflection. So you might have been wondering, well, what if the concavity doesn't change, right? So what if f double prime equals 0 at some number, right? Let's say this is like 3, but then I have concave up over here and concave up over here, right? So even though the second derivative test gave me a place where the second derivative was 0, we would not, so this would be not an inflection point, right? This 3 right here, because the concavity isn't actually changing, right? So like same thing over here. This is kind of similar to when we were looking for relative maxes and mins, right? Think about the case of a basic cubic, something like this, right? We ended up with a point here where the first derivative was equal to 0. However, that point was not a max or a min, right? This point here. And well, that was because we're increasing along this graph everywhere. We don't change from increasing to decreasing, which is what a min and a max should do. So there's sort of similar things going on here, except instead of increasing and decreasing, we have concave up and concave down. Instead of mins and maxes, we have inflection points. So they're kind of paralleling each other here in these sort of exceptions to the theorem, right? So the converse of the theorem, the reverse of it, isn't true. So second derivative test. So yeah, it looks like we've seen this before, right? So if we want to say that a graph is concave upward at a certain point, right, you take the second derivative, f, in this case f double prime, and you plug in whatever value you're looking at. So in this case, just C, some number, right, where we have maybe a min or a max. And that's really all the test is. So I've already kind of gone over that with you guys. And here's a little theorem that sort of goes through it more step by step. Right, so they talk about how the second derivative, if it's positive, you have a relative minimum. If it's negative, you have a relative maximum. And if it equals 0, then the test fails, which is f may have a relative maximum, a relative minimum, or neither. In such cases, you can use the first derivative test. Right, so f double prime of C equals 0 is sort of, in the context of this test, right, this test is only testing for mins and maxes. Inflection points are not within the purview of this test, and so that's why they say the test fails, right? Because the test is meant to tell you if you have a min or a max. That's it, right? We know that if you get something like this, that could be an inflection point. But again, because of the examples we saw before, right, it doesn't have to be, right? You can have the second derivative equals 0 on a place that is not an inflection point. So it's basically inconclusive unless you look at that point more closely and maybe do a first derivative test to the left and to the right. So this one right here, this is meant to be negative 3x to the 5th plus 5x to the 3rd. So find the relative extrema of f of x, right? So we'll use that second derivative test. So to get to the second derivative, we have to get the first derivative. It's going to be negative 15x to the 4th plus 15x squared. And then we want to take another derivative, right? So we end up with negative 60x cubed plus 30x. And this is what we want to use here. So how do we find the extrema? Well, the extrema come from when you set the first derivative equal to 0. All right, so let's see. We get, let's factor out a negative 15x squared here. We end up with x squared minus 1. Right? Right, so we end up with this, x minus 1 times x plus 1. We can factor that with difference of 2 squares. So we have 3 critical points. 3 critical points here. That's going to be 0, -1, and 1. So that's nice and easy. So how do we know what is what, right? We have a degree 5 polynomial. This is a quintic. So it's going to have maybe 4 turns to it at most. In this case, maybe only 3. I guess we'll see, right? But we have to run the test. So what do? Well, we just evaluate the second derivative at these critical points. Right, so the second derivative is -60, -1 cubed, plus 30 times -1. And we get 60 minus 30. Right, so this is going to be 30. So this is a place where our graph is concave up, right? Because that number is positive. Let's try 0. So we get -60 times 0 cubed plus 30 times 0. Well, we get 0. So this is an inconclusive point. Right? We don't necessarily know what's going on over there. Could be an inflection point. We don't know. And then f double prime of 1 is going to give us -60 plus 30, which is -30. Right, so this is concave down. And so what we know is, well, if we have a concave up point at -1, that's going to be our relative minimum. Right, because we have something that's like this. Right, over here we have something like this. So the 1 is going to be our relative max. Right. And then the 0, what we might want to do is sort of test out maybe some values. This one will be kind of tricky to do unless you have a calculator. So let's see what they say about that 0 point. Yeah, so it looks like they just sort of stop there. They say that the test is inconclusive at 0, right? But they do find the relative minimum at -1, which is exactly what we found, and the relative maximum. So they say that you can use the first derivative test to observe that f increases to the left and right side of x equals 0. So maybe what we might want to do is sort of verify this. So let me take the second derivative. The first derivative. We got to use the first derivative. So -15 x squared, so x minus 1, x plus 1. Let's sort of verify what's going on to the left and to the right of 0. Right. So again, what we don't want to do is we don't want to choose a number past -1 or past 1, right? So we want to choose something in between. I'd probably choose -1/2. Right? All right, let me mark that on this right here. Probably choose -1/2 and +1/2. We don't even really need to know the answers here. We just need to know what is the sign of the answer, right? What is it positive or negative? So f prime of 1/2 is going to be, looks like -15/4 times, this will be -1/2 times 3/2. And so this is going to be some positive number, right? So positive slope to the right. And then if we plug in -1/2, right, we're testing, sorry, I should have put this here. We're testing the first derivative on this real number line. Over here, we're going to get -15/4 times -3/2 times, let's see, 1/2. Right, so again, this is going to be positive. So yeah, it looks like what we have here is at 0, we're going to have something kind of like this, right? Where the graph is increasing, right? All these slopes are positive to the left and to the right of 0. So that 0 was an inflection point all along, right? Inflection point. because you can see, right, on the left side, we have concave down. On the right side, we have concave up behavior. So it is an inflection point. And yeah, that's exactly what they have here, right? So we found the minimum, we found the maximum, and then we did some further analysis here to see that that was an inflection point. So it looks like that's all I have for you guys today. So have a great rest of your day.